Hello, testing. Okay.
Good morning, everyone. It's a pleasure to have Chen today, who will speak about logarithmic delocalization of Ising and pots above a floor.
Yep, thank you for the introduction. So I'll be discussing some joint works with Eyal Lubetsky, who was my PhD advisor when I was back in New York, and also with Reza Gaisari, who is at Northwestern. So of course, the Ising model is just a special case of the POTS model, but I write it like this to emphasize that we're not just proving some results in the POTS model that was already known for Ising, but this is really new also for Ising. So these models have already been introduced. So very quickly, the POTS model is a random coloring of a graph. You get to choose from Q colors, and you're penalized by e to the minus beta times the number of neighbors which have different colors. And I will be looking at 3D graphs. So G will always be a subgraph of Z3. And I will take so-called Debruchan boundary conditions, which mean that I will have some kind of box, and half the boundary of the box will be forced to be blue and the other half to be red. And so I'll take beta to be large so that this penalty implies there will be a blue phase and a red phase, which are coexisting. So these are the two pictures to have in mind throughout this talk. One will be red and blue boundary conditions on a cylinder, and one will also be on a cube. So in the cube, 5 sides will have a red boundary condition, and the bottom side will have a blue boundary condition. And I'm interested in studying interfaces which separate these two phases, the red and the blue phase. So in particular, I will define 2 interfaces. The blue interface will just be the boundary of this large blue component. Okay, so you take the blue boundary condition in either setting, you look at the connected component of blue vertices, and the interface is just what separates that component from everything above it. And analogously, you can define the red interface, which separates the red component from everything below it. And I will refer to this left picture as the no floor model and the right picture as the floor model, because this interface, both these interfaces, by definition, they are attached to the place where the boundary conditions change. And so the point is that in the picture on the right, in the box, the place where the boundary condition changes, you will also find this sheet of blue vertices. And this sheet of blue vertices acts as a floor, which the interface cannot go below. So I guess what is interesting to me is the effect of the presence of such a floor. So quickly, so I have these 2 pictures. So you can imagine sampling a POTS model, and this on the bottom, there will be this blue interface, which delineates this large blue component. And it's different from the red component, from the red interface, due to the presence of green, yellow, orange, purple colors, which may be in between. But I say that this is a very misleading picture because the phenomenology in 2D is very different from 3D. So really in 3D, you won't get something so rough like this. You should imagine that you have 2 interfaces which really stick together in most locations, and they just differentiate in a few places by occasional microscopic, say, green bubbles.
So can I just ask 2 questions? The first is what is the actual, what definition of boundary you're using? I always get, are you identifying it with like the vertex boundary or plaquettes?
So yeah, I work with plaquettes. So you can imagine putting a dual plaquette in between everywhere there's a blue versus non-blue. But it doesn't really matter. You can also define it as the upper vertex boundary of such a component.
And in this misleading picture, what are the boundary conditions?
So it will be on the cylinder with red on top and blue on bottom. So this picture on the left. So the no floor setting is quite well known for this open problem of a roughening transition. So this conjecture says that, okay, so we know that at beta critical, the Potts model undergoes a phase transition from disorder to order. And so past beta critical, you can make this well-defined interface, which is meaningful in the sense that it separates two ordered phases. And we know that once you take beta large enough, you will have this flat picture where both the interfaces stick together and are flat. And the conjecture is that once you lower beta low enough to get near the critical point, you actually, even though you have this ordered phases, the interface between them begins to be rough. And this is purely a 3D phenomenon. So in 2D, it will always be rough. And if, as we saw yesterday in Sasha's talk, it should be a Brownian motion. And in 4D and higher, it will always be flat. And this transition really mimics it is modeled by the proven roughening transition that you would find in, say, the height functions, which are similar. So like the discrete Gaussian or the solid-on-solid model. But this is probably the most well-known open problem in this setting. And we are interested not in this conjecture today, but what will happen in the large beta side, but then once you put it in the floor setting. Actually, maybe it will be helpful for me to just draw two graphs to have in mind. So we'll always have, maybe I'll draw it here. We'll have this as no floor boundary, no floor graph, and then this will be the setting. I'm drawing this right. This will be the setting that induces the floor. Okay, so for some background, the breakthrough work in this area is by Dobrushin in the 70s. And he proved that for the Ising model, when you're in this cylinder case, then you have this flat picture. So this is rigidity, and he proved that the maximum in this setting will also be log n. And he did this through a perturbative way of writing the law of this interface. So he says that the law of this interface should be given by exponential minus beta times the size of the interface. So this is expected because everywhere you see the interface, there's a blue next to a non-blue, for example. And then plus some perturbative terms, which come from the fact that, well, the model is not just the interface model, it's the whole 3D Potts model. So you have to account for the partition functions above and below. And this gets encoded by a cluster expansion to some perturbative terms. And he also proves that above fixed points, you have exponential tails on the probability to be a large height, to be for some constant gamma. And recently, this identifying this constant gamma is like a large deviation problem. And this was also done about 10 years ago now. So this picture in the low temperature setting without a floor is quite complete. On the other hand, with the box, once you put a floor, we'll see we know almost nothing. So, from the science perspective, I was told that this serves as a good model for, well, it serves as a model for crystals or bacteria which grow on a physical surface. So there's a physical interpretation of this floor. And from the math side, there's a lot of interesting, mostly conjectured phenomenon. So the first is this phenomenon of entropic repulsion. So what this means is that we saw that when you don't have a floor, your picture is flat everywhere, or almost everywhere. And indeed, if I take this model and I put beta to be infinity, it will just be, the interfaces will just be completely flat at the bottom. This minimizes the energy. But the moment I take beta to be finite, but large, or large but still finite, this rigid surface begins to delocalize. So the variance of, or the height above any fixed point diverges now. So this is entropic repulsion. And then this is really, well, proving this is the first step in a big program of things we like to show about such a surface. So the first picture is showing this delocalizes. And then once you show you have this picture in the left, you can ask what is the shape of this plateau that you see. And so this should have a limit shape of being a translation of wolf shapes. This is the second picture. And then you can also study the fluctuations of the, you know, if you're looking top down, the fluctuations of this plateau boundary around this limit shape. And this should be given by an ensemble of area tilted random walks.
So can I ask about the large deviation? So I'm a bit surprised that there's no relation to surface tension. You have this gamma 4. I mean, I thought that surface tension was really like
so that is related to the cost of creating a surface like this under 1. You would get something like, you would see something, the surface tension will pop up there. But this is talking more about, you should imagine a picture like this, where you're ordinarily flat, and then you want to say, what is the probability that above this point, my interface actually looks like this here? It reaches some large height h. And so this is obtained by just adding 4h bases to your interface. So the cost is about e to the minus 4 beta h. Okay, so we'll just jump right in. So this is a rephrasing of the entropic repulsion question, which is what we are interested in today. This is just saying you have cost model on this box. What's the height of this blue component? What's the typical height of this blue component? So here's the background of all we know. Very easy to say. So for the Ising model, it was proven in the 80s by Forlick and Pfister that you do have this picture of delocalization. But their proof is a soft proof. So there's no quantitative bounds on how fast it is delocalizing. And then on top of that, their proof uses some correlation inequalities which are not available in POTS. So even for general POTS, we don't have anything. And so our theorem says you should ignore the text. It's just setting up the boundary conditions in the graph. But this equation is saying that except for an epsilon fraction of places, my interface lies between, my interface will lie in this interval. So I have an upper bound of 1 over gamma beta times log n, or some gamma, which is about 4. And then a lower bound, which is 1 minus epsilon times that. In particular, this proves logarithmic delocalization for both, well, for general plots. And what will be interesting is establishing exactly what constant should go before the log. And so this will be discussed at the end of the talk. Or maybe for reference, it will also be nice to just write this down. So we have theorem is that the typical height of, say, the blue interface is in this interval. So you have 1 minus epsilon over gamma blue beta log n, and upper bounded by the same quantity without the 1 minus epsilon prefactor. And this upper bound is conjecturally sharp, or so we say. So before I start the proof, this is just a slide to give the impression that although we know almost nothing for entropic propulsion in the 3D Ising model, we know, I mean, since the proof of Boylik and Pfister, there's been much work on studying this phenomenon in approximation models. And in particular, one class of models which will approximate this interface is height functions. And so here you have very, very precise information on the height in the box of these surfaces, of these height functions. And so, so these three height functions are the solid on solid model, which I'll define later. This is the integer valued discrete Gaussian free field, and then the real valued discrete Gaussian free field. And what's interesting to note is that there is a precise relationship between this typical height of this height function once you impose a floor. So here the floor is conditioning to be non-negative. And with the extrema when there's no conditioning. So here, you look at the maximum of these height functions when there's no conditioning, then there's a precise scaling relationship between the two. And what will be important for us is the SOS model, since this height function most closely approximates the 3D Ising model. So this I would also like to write down for later. So it's going to be unrelated to most of the talk and just come in at the very end. So in the SOS model, we have, say, the typical height in the box is 1 over 4 beta log n versus, I wrote the maximum there, but it's really the minimum that matters. So the minimum in the cylinder, which is just my name for no floor, is 1/2 or 1 over 2 beta log n. Also, this is not good. Okay. So the proof will go through the random cluster model, which also has been introduced already in this conference. So hopefully it is the percolation where you put an edge weight of P, but you also add a global cluster weight of Q to the number of connected components in this percolation. So I will call these clusters. And I'll also say that edges are wired generally if they're there. And so what's nice is, so we've seen that this model is coupled with a 6-vertex model, the BKW. Here we use more simple coupling, which is the Edwards-Sokal coupling with the Potts model. So this says if my global cluster weight Q is the same as the Q in Potts, and my edge weight P is 1 minus e to the minus beta, then I can get a Potts model by just sampling a random cluster model and then coloring them uniformly and independently at random. And so you should think that in the background of these Potts interfaces, you have at the same time existing some edge percolation. And the analogous setup, if you just want to study random cluster or to get the random cluster in the background, is to take wired and wired boundary conditions and then condition on them to stay disconnected. And this generates two more interfaces. So you can, just as we define the, say the blue interface, which is, recall you just take the connected component of blue vertices and then take the boundary of that. The bottom interface will just be in random cluster, take the connected component of that bottom wired boundary and take the boundary of that, separates it from everything above it. So you should think of it as just a complete analog of these class interfaces, but we're interested in them because we want to utilize this background edge model. So again, you have these two pictures, which are completely different in 3D, but they're nice to look at in 2D. And they're separated by finite components in the middle, or microscopic components in the middle. So you should think of it as having one model with edges and colors. And again, these in 3D, it's easy to show that in both the two settings, you'll have these four interfaces stuck together in most places. So in particular, the typical height of the four interfaces are the same. Okay, so any questions about this setup before I start the proof? No, so the plan is to prove the lower bound, which is not sharp, but it is, I mean, that lower bound is what shows you have entropic propulsion. And I think it's more interesting. So we begin with the heuristic from the SOS model. So recall you can write the law of the interface in such a form, analyzing by the size of the interface plus some error terms or perturbative terms. So the SOS model, you can define it by just removing the perturbative terms and then also assuming that the surface has a nice geometry, namely that it has the geometry of a height function. And then you get the SOS model. And so we saw that this model says that the typical height should be order log n. And how does that proof go? You can apply a lifting argument, which is really just the Pyers map, but the Pyers map gains from entropy and not energy. So we know that if beta is infinity, you actually are just a flat sheet at height 0. So how do we rule this out? So imagine you start and your height function is just 0 everywhere. So you want to apply the map, which raises the height function by 1 everywhere. And that will cost you e to the minus 4 beta n, because you add 4 faces to this surface. 4 n faces to the surface along the boundary. But then you would like to gain from your ability to have your downward fluctuations now. So when you are flat at height 0, you have no ability to go down at all. But now that I have raised myself up by 1, I can drop back down to 0 in any of the n squared places. So anywhere where I choose to drop back down to 0, I add 4 more faces to my interface. And so this costs me a e to the minus 4 beta. But the point is I can choose to do that in each of the n squared locations. So that choice is like a 1 plus e to the minus 4 beta factor. And then to the power of n squared, because I can make that choice in each of the n squared places. So in general, if I want to go from height h minus 1 to h, the boundary cost is still the same. It costs me 4n to lift by 1. But now to realize the new space I've gained, I need to go all the way back down to 0. And so this gain in entropy gets worse and worse. It becomes a e to the minus 4 beta h. And okay, of course, 1 plus that to the n squared is just exponential of e to the minus 4 beta h times n squared. And so this is basically saying it's more beneficial for me to rise and rise and rise until these two terms become the same. And this happens exactly when this second exponential in the entropy is order n, which is when h is 1 over 4 beta log n. And so this argument is it's quite sharp. It gets you the reality, 1 over 4 beta log n. So the issue with this in 3D Ising is these perturbative terms. In fact, you can see that, well, I'm not showing you, but what happens is these perturbative terms, I mean, you should think of them as encoding some interaction terms. And there's an interaction between this interface and the floor due to the ability to put in, due to the partition function below the floor. And actually, the size of these interactions is going to be the same order as the size of this gain in entropy. The point that you cannot tell which one is bigger. And so what happens is that when you try and run this argument, the second part of this, realizing this gain in the entropy will still be fine. But now when you ask what is the cost of this map, which just lifts everything up by 1, well, you're not only paying around the boundary, but you're also paying this interaction term where the interface is now at a different location with respect to the floor. And so this payment, if you don't take care of it, will kill this argument entirely. So that means that our goal is to show that this cost of lifting up is not actually going to kill us. And so we will do this by showing that the cost of this lifting map is lower in this box setting. Is lower in this box setting where you interact with the floor than it is in the cylinder setting where there's no floor to interact with. And so it really will just be e to the minus 4 beta. So that's captured by this inequality. So I can fix an interface I and look at theta I, which is just lifting it up by 1. And I want to say that this term on the left is not too small, right? So if this ratio on the left is small, that means that the weight of theta I is really, really small. So it's really costly to get to theta I. So the point is that we will switch what we are comparing. So this top inequality is saying we should fix a domain and then compare the weight of two interfaces. So this is what Dobrushin's cluster expansion form is good for. And that is too hard to work with. So instead, we're going to do a swap and fix an interface instead and compare its weights under the two domains. And this is nice because you can view this box domain, right, as just taking the cylinder graph and, well, okay, actually before that, I should say that for reasons I'll discuss later, it's important right now that we move to the random cluster interface and work with that instead of the class interface. But so in the random cluster perspective, this box domain is just the cylinder domain, but I just enforce this sheet of edges. So at height 0, I just put an edge there with probability 1. And that gives me the box domain. And if I put them there, if I don't put them there, so I put them there with probability 0, then it's just the cylinder domain. And so then I can interpolate between the two by adding them with probability S. And then now I want to compare these two terms. So we have two quantities. We want to compare at 0 and 1, then I can take the derivative and integrate from 0 to 1. And what's nice is these expressions are going to be given by partition functions. So when you take the derivative of a partition function, you just get some kind of expectation. Here will be a probability. So skipping all those details, the point is that this inequality, to prove this inequality, it reduces to comparing the probability of edges being open in two graphs. And so I have a picture, don't worry. So what it reduces to is you have some interface on the left, and you look at the graph induced below this interface. So we call it, by the definition of this top interface, it is the boundary of this top connected component. So once I reveal that, I reveal no information about what's below me. So it induces free boundary conditions. And so I have this graph, which is some mixed free and open boundary conditions, but the point is just that it's a bona fide random cluster model with no additional conditioning. And I have some edge at height 0, and I want to compare the probability that it's open compared to the graph on the right, which is just everything shifted up by 1. Now, by monotonicity, the inequality that I want to show is true if these two subgraphs are comparable, in the sense that if the graph on the left is entirely contained in the graph on the right, then this is just true by FKG, because my free boundary condition is further away on the right. So that's more positive. But we don't have this isn't true in general because we're not a height function. So in this example, if my purple one is my starting interface, and then I lift it up by 1, then you can see on the picture on the right that the subgraph of the left is not contained in the subgraph in the middle. And so I would say our key idea is that we're going to do something a bit strange. So in this lifting argument, instead of lifting my height, or instead of lifting the interface by 1, I'm going to lift it by a huge amount, by log n. And this really is a big amount because my target is something like about 1/4 beta log n. So I'm proposing that in our Ayers map, we lift by way over the target height. And so this is a bit strange because you want, in a Ayers argument, you want the image to be not too rare. But the point is that in this entropic repulsion setting, it is going to be easier for me to be way above my target height than it is going to be for me to be just a little bit below my target height. And this is true in general, I think, in these entropic repulsion settings. And it's because when you're really, really high, the reason it's unlikely is because you're paying a cost along the boundary. Like you've added too many sites along the boundary to lift up. But if you're below the target height, that means that you're too close to the floor. So in the bulk, you don't have enough space to have your downward fluctuations. So being too high is bad because of a boundary term, whereas being too low is bad because of an area term. You have this mismatch. And the point is that once I lift by a huge amount log n, I am avoiding any of these. Maybe I just wrong. Like if I start like this, something like here maybe. I'm proposing that we lift like way up here. So I mean, I can prove a priori that maybe the maximum of this starting interface won't be like log n. I mean, actually, I can take this to be like log to the 10 if I want, where it'll be very easy for me to show that this doesn't exceed that height. So I'm going to lift way above so that this graph here is certainly constructed. But that means that this deals with this monotonicity. I mean, this gives me the monotonicity that I want. And so I'm done. I've proved that indeed it is not going to be too costly for me to lift this top interface. Now, I would mention that it's really, really important that we worked with this top interface in the random cluster model. If you work with the, say, Ising model, and you just look at the Ising interface, you can still run a similar argument. Right? You can add a sheet of, say, plus spins or blue vertices at height 0 and interpolate. And you will get the same thing, but the monotonicity will be, this inequality will be in the wrong direction. So in fact, what this is saying is that the effect of the floor from the perspective of this I-top, this top interface, it's kind of pushing you up. It's saying it's actually easier to lift than if there was no floor. Whereas from the Ising perspective, it's saying that the effect of the floor is kind of pulling you down in some sense. And it's unclear whether or not in either case it is pushing you or pulling you to an extent that it really changes the height in a meaningful way. But still there is this effect. So, okay, I should have been here first. So this is saying that you can use this lifting argument and you will get that the height will be at least about 1/4 beta log n. And you can really, okay, so this term is this 1/4 beta log n. And in fact, you can sharpen this in a way to get something a little better. But the point is that once you prove this for the top interface, the same is immediately true for the blue interface by rigidity. So I'm telling you that it's easy to prove that you can show the 4 interfaces are all stuck together. Okay, so I want to conclude with, so if you follow everything, there's something a little strange going on. I call this paradoxical result. So first, I just introduced this result from, wait, I guess the Q equals 2 is proved not 10 years ago, but more recently. So well, recently we identified this large deviation rate, gamma, which is different for the 4 interfaces. But this is just the probability that you have a deviation of height h that I drew earlier. And if you want to realize the sharp constant before the log here, then this argument won't really be enough, because this argument works with sticking like a straight spike down to 0, hence the 4 beta, because it costs you 4 beta h bases to get down to height 0. But in an Ising interface, you won't realize, like, this is not the way in which you get down to height 0, right? In general, if you are, say, like maybe at height h here, and I want to go from some points down to height 0, it's not going to be a column. It's going to get realized in some random path. And so if you want to fully capture this ability to gain from entropy, you need to realize it via these random paths. But this is entirely captured by this large deviation question. It's saying if I'm at, if I look at my interface and I want to go down the height minus h, what is its probability in this form? And so this was done. And also, what was shown is that this minimum should be of this form, 2 over gamma beta log n. So going back now to this picture, I have that for the blue interface in plots. The minimum should be 2 over gamma blue beta times log n. Actually, maybe you shouldn't focus on that for now. What I want to say is this previous realizing these drops by 4 beta h directly gets you this 1 over 4 beta log n, right? Maybe if I go all the way back here, this is like just plugging in e to the minus 4 beta h, plug in the e to the minus gamma beta h. And this gets you directly what h should be, the constant before the log n for h. That means that, according to that logic, if I look at the blue interface, the correct height should be, instead of 1 over 4 beta, just 1 over gamma beta log n. And that is indeed our upper bound here. So this is why I say that the upper bound that we prove is conjecturally sharp. But what's curious is that this lifting argument you can do for from the perspective of any interface. So from the perspective of the random cluster interfaces, their correct height should be 1 over gamma bot times beta log n, or 1 over gamma top. But I told you that I can show that the 4 interfaces are stuck together, so they all have the same height. And on the other hand, in this work up here, we proved that the 4 rates are different. So gamma top, red, blue, and bot are all different. So there's this curiosity here where they should, the prediction, say from this SOS lifting argument, says that they're all different heights, but then it's really just one interface at the same height. So it's really interesting to me to consider what the right answer should be, or what is the constant before this log. And this kind of, well, okay, this paradox is resolved because of these perturbative terms, this interaction with the floor. It's actually saying that this interaction term must be substantial from the perspective of at least 3 of the 4 interfaces, because at least 3 of the 4 will give you the wrong rates when you run this argument. And maybe all 4 give the wrong rate when you run this argument. Okay, so this is this mystery, which is still an open problem, and I would be very interested in knowing what the right answer is. Okay, so to summarize, you know that one of these 2 things must be true, and they would both be really fascinating to me. So the first case is simply that this conjectured height is wrong. And that would be interesting because, you know, even for Ising, it would be wrong. And then this is like the first step of, right, a big program of things we'd like to prove for 3D Ising, and we'll be saying already for there, the intuition from SOS is a little off. And it's saying that these interactions, which I think are generally believed to not have much impact, really pull the interface downwards. And then the other option is just that the conjecture is still correct. And this is also interesting because this is saying that you have these, at least, okay, for FK Ising, you have still 3 interfaces. And somehow the model is deciding that this Ising interface is more natural. And the height of all 3 interfaces should be determined by the Ising rate. And this is still going to be quite surprising because you can ask this question purely in terms of the FK model. You don't have to define any coloring of vertices at all. You can just say you have this FK model with wired boundary conditions, condition to disconnect. And then if you ask what is the height of the interface there, it's going to be given by the Ising rate, some large deviation rate in the Ising model. I don't see any reason why it should be, the model should somehow pick out the Potts rate to be the correct one over the FK rates. But that's what would be implied if the conjecture is correct. So one of these 2 cases must be true, and I think they'll both be very interesting phenomena. And that concludes my talk.
Any questions?
Hi, thanks for the talk. I'm a bit confused with the first possibility. Why, doesn't your theorem say that the prediction is right? Why doesn't your theorem say this?
Well, these 4 different rates are all captured within this interval. Yeah. Well, actually, you can rule out one of them. You can rule out the gamma bot. But so it's kind of like 1 over gamma bot would lie above this interval. So we can rule that one out. But basically, this you should replace by 1 over gamma top. So you have a lower bound by the heights predicted by the top interface and an upper bound by the height predicted by the blue interface. And then we can't rule out, well, yeah, we cannot identify which one it would be, if any.
Thanks. My next question is, which do you think it is?
Yeah, so I personally, okay, amongst the 3 of us who wrote this paper, there is a disagreement on which of these 2 cases we believe is true. I believe, personally, the first case is true, that this interaction term from the floor really pulls you down, simply because I don't see why this model should spontaneously pick out one of the 2 models as being more natural. But there is, I mean, I can give you more details later, but I think there are substantial arguments for both. So it's really unclear. We're in disagreement on which we believe is true.